Bismillahirrahmanirrahim. Lecture number 15 of the waves and oscillations. In this lecture we will be discussing about the transverse velocity of a particle. As we have already discussed that the waves produced on a stretch string are known as the transverse waves, and we have also discussed about the sinusoidal waves. So if the transverse waves are described by the sinusoidal function, sinusoidal means sine function or the cosine function. So how we can determine the transverse speed of the particles of the medium at any position x in time t in a one-dimensional wave. So let us consider a wave that travels along a string like this one, and the wave is traveling with a speed v to the right side along the x-axis, while the particles are oscillating along the y-axis with a speed u. So as we know that the vertical displacement at any time t in any position x is given by a sinusoidal function, that is y is equal to ym sine of kx minus omega t. This is the displacement of the wave. So we know that velocity is the derivative of the displacement, or the rate of change of the displacement. So we can easily find the vertical velocity of the particles of the medium as a function of position and time. Position means x coordinate over here. So u of x and t, and that is the u is the speed, the velocity of the particles, not the speed. Y, the subscript y show that it is along the y-axis. So the vertical velocity can easily be written as curly y over curly t. So that is curly over curly t of ym sine of kx minus omega t, and if we differentiate it, so we get cos of kx minus omega t into minus omega. Where here you see that the net result is minus omega ym cos of kx minus omega t. So this is the velocity of the particles of the medium along the y-axis. Where here we are seeing a negative sign. This, if the velocity of the particle is downward, it will be negative, and if it will be upward, it will be positive. That will be determined by the cos. The positive, when the velocity, the particle is moving upward, its velocity will be positive, and this whole quantity should come to be positive. So the cos will give a negative sign in that case. We can also find the acceleration of the particle along the y-axis, because we know that every particle of the medium oscillates, or more precisely every particle of the medium will perform a simple harmonic motion along the y-axis. So to find the acceleration, we take the second derivative of the or displacement with respect to time, and that gives us minus omega ym minus sine of kx minus omega t into minus omega, which is minus omega square ym sine of kx minus omega t. As we know that sine of kx, ym sine of kx minus omega t is the displacement itself, that is the y of x or t. So ay, that is the acceleration along the y-axis, the vertical acceleration of the particles of the medium, is going to be minus omega square y. In case of the mass spring system, we have seen that the acceleration is minus omega square x. That is, the acceleration is always proportional to the magnitude of the displacement and is in opposite direction always. That is, the acceleration is always directed towards the equilibrium position in a simple harmonic motion. So the motion of the particles of the medium through which a wave is traveling is of the simple harmonic motion. Remember that this transverse velocity uy of the particles of the medium should not be mixed or confused with the speed of the wave, that is v. V always represent the speed of the wave, while u, we will represent the vertical velocity of the particles of the medium with u. V is the speed of the wave and represents the entire wave. It depends on the properties of the medium and not on the other properties of the wave. It is constant for the same medium. That is, the v, the speed of the wave, or the phase speed, is constant for the same medium because it depends on the properties of the medium and not on the properties of the wave. uy is the velocity of each particle and is independent of the other particles. It depends on the x coordinate as well as on the time. So uy depends on the angular frequency omega and also on the amplitude, while v is independent of such quantities. Now we are going to discuss another important thing, that is the phase and phase constant. So to elaborate these things, let us consider a sinusoidal wave given by the equation y of xt is equal to ym sine of kx or minus plus omega t. The argument of the sine function, in this case, that is kx minus omega t or kx plus omega t, is known as phase of the wave. This wave function is a particular type of a function that represents that at x is equal to 0 and t is equal to 0, the displacement y is always 0, but it is not the general case. That is, all the waves should not have a 0 displacement at t is equal to 0 and x is equal to 0. So we include another quantity in the argument, that is to represent the general waves. Y is equal to ym sine of kx minus omega t minus pi. Now the whole quantity in the parenthesis is said to be the phase of the wave, while this pi is said to be the phase constant. Now, if you put x is equal to 0 and t is equal to 0 in this equation, this gives ym sine of minus pi. So, which is not necessarily 0, means ki the displacement is not necessarily 0 at x is equal to 0 and t is equal to 0. This phi is the phase constant. So this is very easy to differentiate the phase of the wave and the phase constant of the wave. The whole argument of the wave function is said to be the phase, while the quantity other than kx minus omega t is said to be the phase constant. Two waves with the same phase or a phase difference of 2 pi, 4 pi, or any integral, even integral multiple of n pi, that is 2n pi, are said to be in phase. That is, the waves having phases kx minus omega t and kx minus omega t minus 2 pi, kx minus omega t minus 4 pi, kx minus omega t minus 6 pi, or kx minus omega t minus 2n pi will have the same displacement at the same position in time. So we say that these waves are in phase. The phase constant pi does nothing with the shape of the wave. It just displaces the wave in position coordinates, that is, it moves the wave to the right or to the left in the space coordinate, or in the time coordinate. For example, the waves, two waves, ym sine of kx minus omega t and ym sine of kx minus omega t minus pi will have the same shape, but one may be forward or backward of the other in space or time coordinate. To elaborate this, let us rewrite this equation number 3, in two different forms. Like this: y is equal to ym sine of k. Generally it was kx minus omega t minus pi. So we include that minus pi in the first term and take k is common. So this is k into x minus pi by k minus omega t. And this one is ym sine of kx minus omega t plus pi by omega. Now, what happens? The first case, look at this equation and the two waves, sine of kx minus omega t, and the other one, sine of kx minus omega t minus pi. Look at this. In this wave, the blue one, at x is equal to 0 and t is equal to 0, the displacement is 0. And as the x and t the x increases, this one we take at a particular constant time. We take the wave at constant time, that is a snapshot of the wave at a particular instant. So this wave is represented by this blue curve, and if we include a phase constant pi like this, that is this equation, at any particular time t. So this shifts the wave in k space by an amount in phase, not in k space, in position space, or the position coordinate, by an amount pi by k. That is, this the zero, the displacement zero of this wave is at x is equal to 0, while at the same time the displacement of that corresponding point in the red wave is pi by k ahead of the blue wave. That is, it shifts the wave forward in x coordinate by an amount pi by k. So if this pi, we put the pi is equal to 0, then these two waves, the red and the blue one, will merge together. Similarly, if we take a snapshot of the wave in time coordinate, what does it mean? That if we look at the oscillations of a point on a particular value of x, that is at a particular point of x, say this point, we are looking at the waves and we allow the time, that is, you are making a video of the wave at a particular position. So what happens, that the blue wave, this one, and the red one, that is, the red one represents a wave which have a phase constant pi, this one, and this blue one represents a wave that has 0 phase constant. So at a particular position, the red wave arrives, and the crest of the red wave arrives first, while the crest of the blue wave arrives after time pi by omega. That is, the constant pi in this case shift the wave kx minus omega t by a time pi by omega. So we can say that it shifts either the wave in the position coordinate or in the space coordinate, in the time coordinate, sorry. So in time coordinate, look at this point. At the first instance, it appears that the blue one is forward and the red one is after that, but no. Look carefully. This time is occurring before this time. So the phase constant pi shifts the wave forward in time by a time pi by omega.